Hello, everyone. We continue working with partial differential equations. Basically, today we are going to start them. We just did Fourier series, and now we are going to do partial differential equations. One of the objects which is described by partial differential equations is a string. It's motion of a string. So what I'm going to do, I'm going to show you a short, very short, like several seconds video on how the guitar string is vibrating. Okay, give me a second. So let's that's a very short video, you see. Okay, one more time. Now, guys, I'm moving back to our class, and give me a second. So, well, this is 10.7 actually. Let me kind of move my controls up. So, 10.7 vibration of an elastic string. And let me make it a little bit bigger. So let's see, it's like a title of our section, vibration of an elastic string. Okay, we've just seen how guitar strings are vibrating, right? They kind of go like, if you put guitar like vertically, like normal people do, right? The strings will go like up and down, right? And you see that like oscillations are in the beginning, they look a little bit strange, but finally they become like a sinusoidal function, right? So what I want to do, I want to draw a little guitar and consider a little bit of physics of the process. Just like a little, while I'm drawing my guitar, you can kind of watch something else, right? Okay. I don't know if you can see anything actually. I really don't see. Okay. Something does not work. Give me a second. Okay, let me draw a guitar. So guitar is going to look like this. Well, I'm not a very big artist. I've seen that you guys draw very nice cats, but if I draw a guitar, I'm not gonna draw anything super beautiful. So it's approximately like how guitar is going to look. I don't think that it has this thingy. Supposed to be something like this, right? And well, there's a hole somewhere here, right? And the strings. Well, I'm going to just draw one string, okay? Let me change the color and draw one string. First, I'm going to draw a straight line, like the string in the beginning. I know that it does not actually does not attach over here, but let's just kind of for simplicity of the picture. So this is undistracted string, right? Now imagine that we kind of pull it up somewhere. I don't know, we can pull it up. Usually pull it up over here, right? So something like this, and maybe kind of a finger. Somebody pulled it up. Well, eventually, guys, what we are going to do is a sinusoidal oscillation No, the orange, we already used the orange. Let's use blue. So eventually what is going to happen to a string, it's going to develop something like this. Well, it's not going to be that big as I have it on the picture. You've seen oscillations are kind of small, but still, if you do slow motion, it's visible. Give me a second. Let me. I cannot. Okay, let me just turn it off. I don't see like what my camera is showing. Okay, well, we don't need that right now. So that's a string, right? What I'm going to do, guys, I'm going to draw like a system of coordinates here to kind of show the string. Imagine that initially string is located like attached over here somewhere and attached over here somewhere. I'm going to use variables x, which is going to be, well, give me a second. It's going to be like a spatial variable, like the length of the string actually, right? And I'm going to use variable u, which is going to be the vertical deflection of the string, like I'm going to draw something. Okay. I think it's not copy what I have on the top, but that's something like this. A string is doing something like this. Okay, so u is going to be like how far away from x-axis it went up. U is going to depend, you've seen already probably in the picture, like on the video, that U is going to depend on two variables, and they are going to be variables of like position and time. Let me kind of write it down one more time. U is going to depend on X and on T. So X sits over here. T, I cannot draw T here because it's two-dimensional graph. So it's just like for different T's, it's going to behave something like this. I'm going to draw just one more kind of position of the string, which can be like for a different moment of time. So, sorry. It's going to erase the whole thing, I guess. Right, and that's erased. Of course, it's erased my x-axis, which was not fair, and that even more. Okay. Now I have to draw everything again. It's my axis. Okay, I'm not going to change the color. I'm just going to use the same one. So for different t, that's going to be like two different times. I'm going to label the top one T1 and the bottom one, this one is T2. So these are kind of pictures for different times. I cannot draw the time that's supposed to give me three-dimensional graph, right? So U is a position. That's how far away it's up. So point over here with coordinate x is going to have coordinate u over here. Now, guys, I'm going to explain you how equation is obtained. If you don't like physics and you kind of don't feel like you want to learn how it's obtained, it's not necessary right now. Eventually, if you need it, you are going to learn it. So for the next like 10 minutes, you just can like skip the video and start the video again where I say separation of variables. I'm going to explain how differential equation in partial derivatives is obtained for the string. So I'm going to cut a little piece of the string. Well, I don't know, maybe like over here, I'm going to cut a little piece of the string over here, right? This one. And I'm going to enlarge it. I'm going to draw it bigger. It's going to be like big piece of the string. Okay. Well, why actually the string is going to oscillate? Well, you know that the string is oscillating because it has some tension in it, because you actually stretch it, right? Otherwise, it's going to just move and stay there. Something makes the string go up and down, and that's a tension force. So we do have tension force, and that usually works along the string. So we have tension force here, and we do have tension force here. Well, we don't know what is going to be the angle here. I don't know. I'm going to just label it with, let's say, alpha. and this angle is alpha 2, and I'm going to label this is alpha 1 and this is alpha 2. Why are they going to be different? Well, you see that if you draw a tangent line to a string over here, for example, and over here, they are going to be different tangent lines. So actually, they are going to be two different angles here. Well, the string does not move horizontally. It does not move like along x-axis. It actually moves perpendicular to x-axis, right? The motion goes like this, up and down. Up and down means that we do have only vertical component of the force here on this picture. So I'm going to do a projection of a tension force on a vertical axis. So let me choose a different color, and that's going to be projection of tension force. I'm going to label this as force 2, okay? And this projection is going to be force 1. Force 1 goes down, force 2 goes up, right? The piece of a string which I'm considering is going to have length, this distance, is going to be called delta x, or same as dx, okay? Well, what I'll need also introduce a linear density of the string, linear density. Linear density. What is linear density? Well, you take the whole string, put it on scales, and then take a ruler and measure how long is it. Divide mass of a string over length of a string, and you are going to get linear density. Linear density shows how much one unit of a string weighs. For example, your string weighs like 2 grams, and the length is, I don't know, 3 meters. Which means that if you divide 2 grams over 3 meters, it's going to be 2 over 3 grams per meter. That's linear density. So this is total mass. Total length. Sorry. Total. Click this. Total length. Okay. So what are we going to, how are we going to use this linear density? Well, I'm going to calculate the mass of this piece as delta m, which is going to be equal the size of the piece, delta x, multiplied by linear density. Well, if you kind of move the length over here, that's going to be the linear density multiplied by the size of the string equals to the mass. But if you cut a little portion of a string, for example, I don't know, 1 centimeter, well, you multiply density by 1 centimeter, you get how much it weighs, right? Okay, what I'm going to do now, I'm going to write down second Newton's law. And I think I'm going to move to next page just because I don't have any space here already left. So next page, second Newton's law. Well, you probably remember from somewhere in like high school or middle school that F equals ma. So if something is moving with acceleration, then there is a net force, and this net force is proportional to this acceleration with the coefficient of a mass, right? So I'm going to use this second Newton's law for our piece of a string. First, I want to like calculate like my force. So what is going to be my force? My force is going to be the net force. I'm going to call it net force. Maybe I should write down net over here too, equals F2 minus F1. Like I subtract the forces, and that's because they are opposite direction. You can subtract 1 from 2, does not matter actually. I'm going to write that it's tension over sine of alpha 2 minus tension sine of alpha 1. Okay, I'm going to work with force a little bit and then write down this equation. So I'm going to take tension outside, and instead of sine for small angles, and angles are really small, actually if the string is moving, the angle over here is going to be like this, very small. For small angles, sine is approximately equals to a tangent alpha small. For or small angles. So I'm going to write down that it's tangent of alpha 2 minus tangent of alpha 1. And, well, how are we going to calculate this tangent? So remember that tangent is actually a derivative, right? Derivative of a function. Well, just like the slope of the line or derivative of a function equals to tangent. So because my function depends on two variables, x and y, I'm going to take partial derivative. Well, if it was function of just x, I would just differentiate u by x, and that's going to give you tangent here and tangent here. But because my function depends on two variables, I'm going to write down partial derivative, du dx. Well, again, partial because there are two variables, right? And I'm going to put over here 0.2. I don't want to write down like indexes and everything. And then du dx at 0.1. So 2 and 1 are just like endpoints of the string. And, well, what is 0.2 actually for x? It has coordinates, for example, x plus delta x. And 0.1, kind of beginning of the piece, is just x. So, well, I'm just going to kind of plug that thing in and start working on this side, like MA actually. So right now I'm working over here, right? I'm working on a force. Now I'll need to work on MA. So it's T, I'm going to write down du dx at x plus delta x at the point x plus delta x minus du dx at point just x. Well, again, you can put x1 here and x2 here and x1 here, does not matter actually. So let's work on this side. What is mass of this little piece? We do know that it's a linear density rho multiplied by delta x. Now, what is acceleration of this piece? Well, what is general acceleration? Acceleration is a derivative of velocity and also a second derivative of displacement. Displacement is u, so we will need to take a second derivative of displacement. Remember that our function depends not only on x, but on t. So I'm going to take a second derivative of u by t, considering that there is an x variable, and that's going to be actual acceleration. That's acceleration, that's delta mass, okay? And over here, we do have force. So I'm trying to kind of combine everything together. Okay, we just need one little thing to finish this. I'm going to divide by this delta x, the whole equation. I'm going to keep density over here for now. And try it on like second, sorry. Two, not supposed to come over here. T second derivative equals this t. And over here, I'm going to have du dx at the point x plus delta x minus du dx at the point x divided by delta x. So if you consider that the size of your piece of the string, which we consider on the previous page, let me go back, like the size of this goes to 0 if you bring it to a limit, if you make a limit as delta x goes to 0, consider a very, very small piece of a string. Then what is this actually? What is this? If you take a limit, delta x goes to 0. Well, this is definition of a derivative. Function at point x plus delta x minus function at point x divided by delta x, that's just a derivative. That's just like, because my function is already a derivative, so it's going to be a second derivative. So I'm going to write it down as t d second derivative of u by dx2. And we are almost done. I'm just going to move now my density to the right side, and we got our equation of a string. Well, I think I have a little bit of space over here, so I'm going to just use a different color and write final equation over here and maybe circle it. So we have d second derivative of u by dt second derivative equals t over rho d second derivative of u by dx second derivative. So this is equation of a oscillation of elastic string, and you are going to see it written in a shorter way as well. People are going to label this ratio of t over rho, they're going to name it a square. And they're going to write down the equation like this. U t over here equals a square u x. Well, this is a shorter way, right? T small indexes means that you take partial derivative by t twice, partial derivative by x twice, and this is just like a coefficient which depends on how strong you kind of stretch a string and how heavy is the string, which can be any number basically depending on like what are your abilities of load the string and make it heavy. Okay, so now I'm going to move to our next page and kind of set up a problem for which we are going to work on. Give me a second. I want to kind of do the give me a second. So we are going to solve equation second derivative by t equals a square, second derivative by x. Well, usually equation does not come by itself. It comes with some kind of initial values or boundary values. So what do we have? I'm going to start with boundary values. You probably remember that our string is tied to the guitar at 2 points at the beginning and the end, means that we are going to have a certain restrictions on position of point 0 on the string. So like the point with x coordinate 0, no matter what is time, is not going to oscillate. It's going to sit connected to the guitar. The point with position like, I don't know, let's call it L, length of the string, and any time is going to be also connected to the string, to the guitar, right? So these are boundary conditions. Well, depending on what kind of, how do you connect the string, boundary conditions can be different, but we are going to consider this particular case. Boundary conditions are like 0. Now, besides boundary conditions, what we are going to have, remember that we can kind of, how the string starts oscillations. Well, we stretch it somewhere. So this is called initial conditions, right? Initial conditions are going to depend on x and b at 0 moment of time. Here, my time is equal to 0. And it can be some function f of t. Like, for example, on my picture, on my previous picture, let me go back to it. On my previous picture, initially it was like a triangular function with kind of shorter side here and longer side here. So this is my f of t. Let me maybe kind of, I'm going to say this is my f of t. Okay, and let's go back to the well, because equation of a second order about t and about x, so we are going to have like two conditions for t and two conditions for x. So what else can we define? We also can define, sorry, it's supposed to be green. We also can define derivative. Derivative, depending how derivative is initially, like with what kind of velocity you started oscillations. I'm thinking that I should write down partial derivative. If I just write down like a little bar, it's not going to be very clear what derivative by what variable are you taking. So can be a function, also function g of x. So what these two last lines mean actually? Well, the first line shows like what shape was the string at the beginning of the motion. Second line shows if you give any initial velocity, not only kind of change the shape of a string, but you also can push it a little bit. Normally, like for guitar string, I think you just stretch it and release it. But some other strings can be moved with some velocity. So basically we are describing initial velocity of a string. You see that derivative by t at a velocity at a 0 moment of time. So these two conditions are initial conditions. Well, initial conditions logically, right? Time does not have the final condition. And these two are boundary conditions. Well, logically for space, we don't have like the first like initial condition, right? With where the space starts. Well, now guys, we usually, of course, we don't start with the most complicated case. I'm going to start with a case where there is no velocity, just like a guitar string has no initial velocity. Both functions, I forgot to say this, but supposed to say this, both functions f of t and g of t must satisfy these boundary conditions because, well, you cannot like detach string, like move it somewhere, like bend in a sort of shape and then release it and immediately attach it to the guitar. So actually, I'm going to write it down that f of 0 and f of L must be equal to 0 because the string, no matter how you bend it, supposed to be still attached to the ends, like to the guitar, right? And you cannot move these 2 points, end points either. So g of 0 equals g of L, and it's supposed to be equal to 0. So derivative, the velocity of the point which is attached, of the part of the string which is attached to the guitar is not going to change too. So they are going to be like equal to 0. And well, okay. So we kind of set up a problem. Now we are going to start solving it. We are going to use a method which is called separation of variables, which is very common method in partial differential equations. Separation of variables. We're going to make an assumption that our u of x and t, function of two variables x and t, can be represented as a product of two functions, big X, which depends only on space variable x. A little bit confusing, x and x, but actually matching name of the function and the name of the variable is kind of going to keep us checked all the time. And the product of big T, which is a function of t, is it always going to be true? No. Some motions on strings are not going to be separable. They're just going to have t and x together mixed. But for this specific one, you can separate variables here from experience. Okay, so this is assumption. Maybe it's not working, but let's imagine that it works. Let's imagine that we can represent it. How it's going to make our life easier? Well, it's going to make our life easier a lot. What do we want to substitute into this equation? The second derivative by t and second derivative by x. They are partial derivatives, but when you differentiate the product, for example, by t, you basically are not going to do anything with x. You are going to just differentiate t. So I'm going to write down these two partial derivatives. So x is like a constant over t, and I'm going to just keep it. And if you differentiate t 2 times by t, you are going to just get a second derivative of t. And because t depends only on one variable, I'm going to put second derivative, just second derivative by t. What is uxx? Xx, now x is a variable and t is a constant. So I'm going to get a second derivative by x multiplied by t of t. Okay, very good. Now we're going to plug everything into the equation, and maybe I should move to the next page. So I'm going to write down that instead of a utt, I have x of x, second derivative of t equals a square x second derivative of x by big T of little t, the product, right? Well, we did not separate variables yet. Remember from like differential equations, how we separate variables? We put all t's on one side, on all x's on another side. So that's what I'm going to do. So I'm going to put, for example, like t's together and like x's together. I'm going to move my a together with t. I know that it's a little bit weird. Why? But, well, kind of, trust me, that's a mathematical tradition. I'm going to keep axis over here. So kind of, I move this x to the right side, this t to the left side, and a move to the another side, to left side. Now, guys, what we have actually, we have two different functions, function of t and function of x, equal to each other. Imagine that you kind of consider one moment of time, like t equals 1 second. You plug in 1 second here, 1 second here, you have certain second derivative, certain function is going to give you a number, right? But at this moment of time, you are not restricted by x, right? X can go like for anything. And to just satisfy this condition, the ratio between x, second derivative, and x is supposed to be equal to the same number, the number which you kind of set over here when you set up little t equals to 1 second. Same is going to happen to x. Imagine that you set up x like right in the middle of the string. It's going to give you a certain second derivative and a certain function. And this number is not going to change because this function is only of little x. If you choose little x equals to something, well, that's going to be the number there. It's going to be just a certain number. And this certain number is supposed to work for all possible t's, which means that actually this ratio is going to be equal to a constant. It has no escape. Equals to a constant. We are going to call this constant minus lambda. Well, now we are ready to solve separated equations. What I'm going to do, guys, well, you see that when you set up this separation, you are going to get automatically two equations. I'm going to write them down. So the first equation, well, should I look at it first? The first equation is going to be about x, right? Second derivative of x equals minus lambda x. So let's go back. Second derivative of x equals minus lambda x. That's my first equation. And let's go back for a second. For t, we are going to have second derivative of t equals minus lambda a squared t. So second derivative of t equals minus lambda a squared t. So there are two equations, but they are about different variables, so we solve them separately. We are going to kind of have like our boundary conditions and initial conditions, because these are two separate equations. We're supposed to have like conditions on x attached to this equation and conditions on t attached to this equation. Well, guys, when we assume that solution can be separated as a product, we're supposed to assume that the initial conditions like are going to have something like this too. So what I'm going to do, I'll need to find initial conditions to write down, like to connect them to equations. I'm going to write down that I'm going to start with my time initial conditions. U of x 0, initial stretch of the string was equal to f of x, right? Because u now is represented as x of x and t, and here is going to be 0, I'm supposed to have f of x here. So like this is going to be one of my conditions. And remember that I wanted to consider the case when the derivative is equal to 0. So I wanted to consider the case when not g prime, g, sorry, when g of x was equal to 0. Well, no initial velocity. So I'll need to have a derivative by t, right, at x0 be equal g of x, and in our case we decided to make it equal to 0, so I'm going to do a derivative here too. So what is going to be, how do I differentiate this by t? I take a derivative of t by t, right? So x is going to be x of x, and t is going to be just derivative, because I take it by t equals to 0. Well, what does it mean? Well, we are not going to assume that x of x, the whole solution, is equal to 0. So the only thing which can make it turn it into 0 is this one. So we have t derivative at 0 equals 0. Okay, well, this initial condition is just going to stay for a while as it is. Okay, so and this is second initial condition. We got two conditions for the second equation. I'm going to kind of put arrow. This is condition for this equation. This is also condition for this equation. Now I'll need two conditions for my first equation. So what is going to happen for x? What's supposed to be for x? Well, remember that we have boundary conditions, and they were, let me start with like normally, let's initial like u 0t, beginning of the string is not moving, and it was equal to 0, right? If I write it down as x of 0 t of t, I'm going to see that if I don't want to have 0 solution, I must choose this one equals to 0. So that's going to be one of my boundary conditions. X of 0 equals to 0. Oh, kind of understandable, right? Also, u of l t, my second boundary condition that the string or is connected to guitar somewhere in a distance L is going to give me basically very similar thing. It's x of L by t of t. And if you don't want to get a solution which is equal 0 everywhere, but if we set up t of t equals to 0, that's what we're going to have, then we're supposed to set up this to 0, and we get a second condition that x of L equals to 0. Well, I'm going to maybe label it same way, bring arrows to equations. So we actually have two second order equations about different variables, but they are just equations which we solved already. And we have like this, the x problem is a boundary value problem, and t problem is initial value problem, right? So one is Sturm-Liouville, one is Cauchy. Well, let's start with x. So what do we have for x? X second derivative plus lambda x equals 0. We just kind of learned how to deal with this, right? We know that solution is going to be what? Well, remember r squared plus lambda equals 0, from where r equals plus minus I square root of lambda. And we are going to have two solutions, x equals like C1. Let's kind of use what we used already, square root of, sorry, square root of lambda x plus C2 sine square root of lambda x. Remember, like in the previous section, this lambda is not the lambda from z, right? That's actually like square root of lambda is mu, right? And because we don't have any real part here, there's going to be no exponential factor in front of it. Normally we have to have e to the power of like lambda t, right? But we're not going to have it here just because we don't have any real part. So now if we start plugging our conditions, we are going to find out that x of 0 equals to what? C1, right? This one is going to be equal to 0, and it's supposed to be equal to 0. So C1 is equal to 0. And x of L is going to be equal what? C2. Well, because C1 is already equal to 0, we don't have this term. C2 sine of square root of lambda L. And it's supposed to be equal to 0, 2. If you don't want to have a trivial solution, if you set up C2 equals to 0, so then we have this 0 and this 0 and the whole axis 0, which is going to give us still string. We are going to set up this one to 0 because we don't want to have trivial solution. I'm going to write down non-trivial solution. Non-trivial. Well, I don't have any space for solution. Maybe it's here, solution. I'll need to move to the next page, okay? Well, you remember that sine is equal to 0 when argument is equal to what? 0, pi, 2 pi, 3 pi. We already know that 0 is not going to work. It's going to give us, again, trivial solution from the previous section actually 2, right? So we are going to set up square root of lambda multiplied by L as pi n. And we are going to say specifically that n is greater than 0 and that real number, I'm going to write it down like not real number, but natural number, like 1, 2, and so on, natural number. Said that it's real number wrongly. And, well, what is going to be the lambda then? Square root of lambda equals pi n over L, or lambda itself equals pi n over L square. Well, we remember that we call this lambda eigenvalue. One more time. And what is going to be this eigenvalue? Remember that for equation, that was a constant to which actually these two things were equal. For right now, we are just going to move to our next equation for t. But here we'll need to write down a solution, right? I'm going to write down that x of little x is equal a constant by sine of pi n over L, supposed to be square root of lambda, right? X. And actually here we have not just one solution, we have like infinitely many of them. So you set up n equals to 1, you have one solution, n equals to 2, another solution. And the constant here is undefined too, it can be any constant. So far undefined. Remember that we did not use all our boundary conditions and initial conditions. All right. Now I think we are going to move to t. I'm going to make a bar over here, change my color. I don't know. Okay, let's use purple. And write down like t equation, how t equation is going to look. So t equation is going to be second derivative of t plus a square lambda t equals to 0. We already found that only certain lambdas are going to work. So I'm just going to plug these certain lambdas. So lambdas are equal actually pi n over L squared. I'm going to plug them into the equation. Well, because for all other lambdas, everything is going to be 0. So these are only possible lambdas. Which is this constant is not actually quite arbitrary, right? It's not arbitrary constant. Well, that's again second order equation which we solve as standard way, right? You set up our square plus, well, a pi n over L square equals 2, 0, and kind of gets that r equals plus minus I. Well, when you extract the square root, well, why it's y? Because you move it to the right side, that's going to have a minus. So it's a positive number with minus. The square root of this is going to be like a complex number. So when you extract the square root of this, that's going to give you a pi n L, right? Because it's a square already. And we are going to write down solution for t of t. Well, again, two functions. This is mu, right, for like our complex solution. So it's going to be cosine of I pi n over L t plus C2 sine of a pi n over L t. We remember that t prime at t at 0, sorry, not at t, equals to 0, right? That was one of the conditions we got from the zero derivative. So the string was kind of curved, but it was not moved initially. So we're going to use this fact. We are going to differentiate this expression and set up t to 0 and define one of the constants. So let me write it down. So derivative is going to be, well, derivative is not going to be that simple. So it's going to be a pi n over L C1, and derivative of cosine is sine of a pi n over LT, and extra minus in front, right? Derivative of cosine is negative sine. And that's going to be about the same thing for this one, just like with plus, because derivative of sine is just cosine, a pi n over L C2 cosine of a pi n over LT. Give me a second. Now we are going to plug in t equals 0. Here, t equals 0 is going to turn this sign into 0, right? Here is going to turn into 1. Well, usually 1 is good, but here 1 is bad actually, because we do remember that t prime of 0 equals to 0. This one disappears because of sign, but this one does not disappear. It's actually going to be equal C2 by a pi n over L. Well, the only way to satisfy it is set up C2 equals to 0. I'm going to write it down, C2 equals to 0. Well, which means that we are going to have only like one solution, C1. We're not going to calculate C1 yet. Eventually, guys, we are going to calculate it. But for right now, we are just going to write down our total solution as a product of two functions, right? I'm going to add one more page and copy like the whole solution. So solution t of t equals c cosine, right, I a pi n over L t. Solution for x of, solution for x of x is c sine of pi n over L x, a little bit different, right? So because u of x and t is a product of x by t of t, I'm going to combine them together. Well, guys, these two are arbitrary constants, so I'm going to unify them together into one. I'm going to set up that c multiplied by c equals to c. Oh, just a new constant, okay? So I'm going to have c cosine a pi n. I'm sorry, I'm copying t part first because it sits on the top, and then I'm going to copy x part sine of pi n over L x. Okay. Now, guys, what we got, the products of these weird functions. These products are called fundamental solutions. They're going to be all independent from each other, and they all are going to solve occasion. So normally, guys, what we do with fundamental solutions, we add them together with different constants, right? It's just like, well, how else? Like all of them, how do we choose one? Well, we still have one more condition, right? We do have one constant undefined. We still have one more condition, which was looking like this. U of x 0 equals f of x, right? Which I did not kind of resolve. Because all functions like this are going to be solutions, I'm going to sum them up. I'm going to write down that this one, maybe, I'm thinking like how to, okay, just I'm going to sum up functions like this, and that's going to be a solution. Maybe before I do the initial condition, I should explain this. Otherwise, it looks a bit weird. I'm sorry. So I'm going to write down that u of xt equals sigma cn cosine of a pi n over L t multiplied by sine of a, there is no a actually, that's just pi n over Lx. Well, why do I put Cn here? Well, for different n's, I'm probably going to have different constants. So to separate them from each other. Now, what are n's? Well, n's are 1, 2, 3, 4, 5. So I'm going to start n equals 1 and kind of to infinity, right? All of these functions are solutions. So the sum of them or linear combination or solution 2 is a solution 2, right? Now I'm going to plug in into U my initial condition for t, like the first one, which I did not use actually. So I'm going to write down that what is u of x at initial moment of time t equals 0. I'm going to label t equals 0 into the function. Well, if I set up t equals 0 into the function, all my cosines are going to become 1s. And what I'm going to have cn sine, these are 1s, they're going to become 1s. Yeah, I'm going to write them down actually. For those people who are reading notes, they will understand. Okay, and it's supposed to be equal f of x. And now, guys, you probably recognize that what we need to do is to represent our function f of x, which is how we bend our string initially, to what? Well, what are those? They are Fourier functions. Well, a little bit weird coefficient in front, but it looks like they're Fourier functions, right? We do have L, we do have X. Well, kind of everything is here. So basically, guys, what we will need to know, if we want to know the constants here, which are going to solve last initial condition, we solved like boundary conditions when we were solving for X, right? And they gave us actually lambda. We solved for initial conditions that the string was not pushed, velocity equals to 0, and it deleted one of the constant for t condition. But the last constant, which is left, is going to be solved from f of t. And actually, it's going to be just a decomposition of my function by Fourier series, and they are going to be the coefficients. Do we know how to calculate the coefficients? Yes, we do know how to calculate the coefficients, right? We basically know everything about this already, and that's why I was teaching this Fourier series before I started doing this partial differential equations. Well, I'm going to write down the formula, but I don't want to consider examples here. Goal of this section is to teach you new method, separation of variables, and to teach you that solution, the final solution of this second order partial differential equation is going to be represented as a series. So the point is not to actually find the coefficients. I'm going to teach you a separate lecture where we are going to find the coefficients. For right now, I'm just going to write down like the formula for coefficients. So how the coefficients are going to look? Well, this is looking like a sine series, right? We do know how to calculate the coefficients. They are what? 2 over L integral from 0 to L f of x sine of pi n x over L dx. Well, I should label somewhere that this is Fourier series. Otherwise, people who are just looking at the notes are not going to understand it. Fourier series. Well, so the coefficients are going to be calculated by this formula. So we solved the problem. Now, if somebody gives us this function f of x, we will be able to calculate how this string is moving. Well, guys, I do not want to do right now any examples. I'm going to make another video where I'm going to do examples. Again, because Fourier series are not very easy to calculate, right? I'm going to consider maybe just a couple of examples. The idea of this lecture is to learn separation of variables. And we are going to use separation of variables almost in every partial differential equation. So just like one of the major methods. So you're supposed to kind of understand how it works. It's not complicated, right? You put like, we already know how to do separation of variables. We started our differential equations with this. So this is kind of new look at old separation of variables. It's going to be a very typical way to solve the problem. Well, there are many differential equations, partial differential equations, which are solved this way, like, I don't know, like vibrations of the disk, vibrations of the rectangle. They are not always going to be in x and t. X and t is like a time problem in one dimension. The string is actually one-dimensional object, right? We can consider two-dimensional object, and we can consider no time, for example, or three-dimensional object. We are using it in so many applications. So if you learned how to separate variables and how to get to the very last line, that's enough for this section. Okay, so that's going to be end, and thank you very much for kind of watching this video. Okay, I'm going to stop it, and well, examples are coming.